So I'm going to be talking about possible future missions with respect to in situ resource utilization, more probably from a human exploration perspective. So one of the first things we talk about when we look at in situ resource utilization is the fact that you want to take a stepping stone approach if you're interested in trying to find and utilize the resources in the solar system. We've broken it up into two different aspects. One is the microgravity environment, and the other is one that actually has a gravity field. From a resource perspective, you'll probably find very similar resources in both of those environments, but we break it up more from the processing and the focus aspects. And at the same time, we're looking at growing over a period of time the type of things that you're doing, the complexity of the things that you're doing, and the scope and the purpose. So for example, looking in the microgravity environment, we would start with the space station and maybe some in-space habitats, looking at things like trash processing, how you might want to extract and move materials under the microgravity environment, and things like in situ fabrication. And then moving outwards into the solar system, there's been discussions about near-Earth asteroid missions, potentially going to Phobos and such. From a planetary surface perspective, one of the first destinations we're very interested in from a resource perspective is the moon, and the poles in particular, the volatiles that have been discussed this morning. So we need to get into things such as the regolith excavation and transfer, the fact that we want to prospect for water ice, but there are other interesting things such as oxygen and metal extraction aspects that we could do on the moon that can allow us to do similar things on Mars. Now, when we talk about resources and actually utilizing them in some future mission, there are three major areas of interest. The first is just understanding the resources, what's there, whether they're minerals, volatiles, water ice, whatever the case may be. How abundant are they? How are they distributed from a vertical and a surface profile? Are they homogeneous or not? As Tony was alluding to, maybe not in the case of polar volatiles. And what's extremely important is how much energy is required to locate and evolve these things. As I heat up these materials, do the volatiles all come off at lower temperatures, or is it sequential? Besides that, we also need to understand the environment and how it impacts our hardware. We heard this morning permanently shadowed craters may be rich in volatiles. However, if you're operating at 20 to 100 Kelvin, that has some significant challenges on the hardware. What's the local temperature, illumination, and radiation environment? How does that change the physical mineralogical properties of the local regolith and such? And are these volatiles detrimental to processing? The mercury, the sodium that may be in these volatiles. How do I deal with those as I'm trying to get the water that I really want, for example? And then as we go through this stepping stone process, every time we fly a mission, we need to think about what's going to happen next. If I do this first mission and, for example, I drill and determine how much energy it's going to take, how does that prepare me for the next mission where I may actually want to have a larger drill or something like an armed scoop? How can I effectively separate these resources and volatiles? Can I go through repeated cycles, and how does that impact my hardware? For example, the SAM instrument from a science perspective, you want a clean crucible, one-shot deal. Well, from an ISRU perspective, I'm going to be using the same hardware over and over again, so I may want to understand that impact. So when we look at in situ resource utilization, we have what we call the mining cycle, similar to what happens on Earth. Another way to look at it is prospect to product, where you start at the global resource identification. We heard a lot about that type of data from the different missions that have flown, especially LRO has provided a huge data set, but Lunar Prospector, Clementine, Selene, and such have also. Once we've identified these regions of potential interest, you go down to the local resource exploration and mapping. From that data, you can then, once you understand the local resource and the topography, you can start going into the mining operations, the crushing and beneficiation, and the processing aspects. But what's key to all of this is that first couple of steps, the resource assessment or the prospecting. You want to be able to select your sites for prospecting with all the data that you collect up here from a global perspective. So the first step then is performing an exploratory assessment of that region, maybe a short duration mission, maybe penetrators and such. If the data looks promising, you then would perform a more focused assessment, understanding the distribution of those resources, and maybe examining some early mining techniques. And if all of that works, you actually start mining the product. If at any one of these points in this situation you get a null answer, you have to go back and think about how you selected that site in the first place, and maybe you have to go to another site. One of the questions that I was asked in this presentation was, how do you determine what's an operationally useful resource or deposit? And so, for example, when I talked about the preliminary assessment, maybe we look at something on the order of a few kilometers. We try to make hypotheses before the mission as to where the resource might be, and then for a reasonably short duration mission, you try to examine that hypothesis, examining features along the way. Here's Tony's possible model with respect to what we might find as we're going along. A big question, though, will be trying to assess if I have lots of discrete sample points. Am I actually seeing something like this where I got lucky a few times, but the resource is actually pretty distributed, or is it more along these lines? And so, that will take more exploration and a larger data set. Now, what is operationally useful depends on what you want to use the resource for. When we looked at constellation, for example, for the moon, our only resource need from an ISRU perspective was to provide 1,000 kilograms of oxygen per year for life support for a crew. Not really a lot. When you look at this and I take the worst oxygen extraction from regolith model or process that exists, that's basically scraping the surface of a football field over a year, and I can get that much oxygen. Not a lot. However, when you start thinking about using it for propulsion systems, taking a lunar ascent vehicle to low lunar orbit or to an L1 location, you start getting into significantly more amounts of product per year. So if I do 2 missions per year for a reusable lander, that's 60,000 kilograms of oxygen and hydrogen potentially. That would be a much different answer in terms of operationally useful resource than if I only need to get 1,000 kilograms per year. So a big question about the moon, and if I'm looking at propulsion systems, is do I just go for the oxygen alone from the regolith? Oxygen obviously is over 40-some-odd% across the poles and different forms of minerals. Or do I go to the polar regions and try to get the hydrogen, the water, and other volatiles that may exist there? So one of the things that we've been considering is trying to do an early mission that kind of starts looking at both pathways to scout out both what the resources might be at the poles, as well as starting to consider maybe what the economics are associated with oxygen extraction. Depending on this answer, you may go down one of these 2 paths. In either next case, you probably want to do that kind of assessment and critical function demonstrations leading to pilot operations before full-scale use. a lot of discussions about where the water may be coming from in different data sets. This is just a very simplified approach from an engineer's perspective as to, what are the possible sources of the volatiles that exist on the moon, where are they located, how deep are they, what's the environment associated with them. And what's really exciting is the L-cross data that Tony has pointed out, 3 to 10% water plus some other really interesting volatiles. If I have a carbon source like carbon monoxide or carbon dioxide in water, I basically have a petrochemical industry on the moon. I can do plastics, I can do propellants. Ammonia is a really interesting possible product from a life support perspective. The nitrogen and the hydrogen could be extremely important. Now, there's been some really interesting aspects in terms of the hydroxyls that may exist. Look, the frost in some of these craters, the M-cube mobility water at the poles, that may be something of interest, and maybe I can get both of these on an early mission. This is a debate that's going on that if neither of these two answers give me the useful resource I want, do I really have to go into a permanent shadow and look for the deeper ice? So here's those 3 steps again: the exploratory assessment, a more focused assessment, and a mining feasibility. And so from the exploratory assessment, we're looking at basically a very short duration mission, maybe in the sunlight, but for a region that does not have a lot of sunlight for most periods of time. Possibly operating for several hours in a shadowed area that never sees light, if we can find that location near each other. Validate the hardware, evaluate the physical and mineral properties of the regolith, and try to look at a region somewhere on the order of 1 to 3 kilometers using neutron spectrometer, near infrared, to kind of help locate where the hydrogen sources may be, and then 3 to 5 coring operations 1 to 2 meters deep. And while heating those cores, looking at it from a gas chromatograph mass spec perspective. And there are 2 missions that may be looking at that. One is Resource Prospector, that I'll talk a little bit about, that NASA's considering. The Russians are also considering a Luna 27 mission as well. A more focused assessment deals with a much more longer duration mission, possibly 6 months, staying for long periods of time, determining, again, spending more time trying to understand the difference between this kind of response and this kind of response with many more drill sites and more data sets. The RLEP-2 mission was along these lines, that considered a nuclear power source for 6 months to a year in a permanently shadowed crater. This helps you map out the location and concentrations of those volatiles. Now, whether you can do this third step, the second and third step at the same time or different times is a question, but you then want to basically look at what's the feasibility of mining that resource and extracting and separating it? Is the mercury, is the sodium, are the other volatiles that exist going to foul up my system to such an extent that I can't do mining for long periods of time? And so one of the things we're looking at now is called the Resource Prospector mission. A mission concept review is scheduled for September. If everything is go, we potentially may be heading towards a flight in 2018. It's basically an international mission at the moment between NASA and the Canadian Space Agency. And its primary purpose is basically to verify the existence and to characterize water and potential volatiles at the lunar poles. So we want to map the surface distribution of the hydrogen. We would like to try to determine the mineral and chemical properties of that regolith as well, measure the bulk properties of the materials in the core. We want to heat up the cores that we take up to at least 150 degrees centigrade and see what comes off. And we want to determine an extensive amount of volatiles using a GC mass spec. I doubt all of these things will be there, but it's designed to be able to measure these type of constituents. At the same time, we may be releasing some volatiles that that the hardware may not like very much: hydrogen fluoride, hydrogen chloride, and ammonia. These two, one of the things that we're looking at is a second step, which is actually demonstrating how I might extract oxygen from lunar regolith using what's called a hydrogen reduction process, where you heat up the regolith to basically 900 degrees centigrade, add hydrogen to it, and if there's any iron oxide in the regolith, you form water. Problem is when you heat up anything to 900 degrees C in the presence of hydrogen, hydrogen likes to react with it. So we have found that small amounts of hydrochloric acid, hydrofluoric acid, and hydrogen sulfide have been created when we've heated up lunar regolith. This is what the Resource Prospector mission looked like back in July of 2012 when we performed a field demonstration of the mission concept in Hawaii. This is not flight hardware, but it is flight functional. And we were able to put all the hardware that we needed to do on the mission on a single rover. If you've seen some of our past presentations, there was a much larger rover in the background carrying extra hardware sometimes. But basically the idea was to show all of the operations that we would do in a very short period of time, 5 to 7 days. We basically start out with a neutron spectrometer that examines the minerals and whether there's OH or water on the surface. We have a neutron spectrometer that looks at the subsurface down to about 1 meter, and our rover speed is based on allowing us to look down to about 1 meter. If we find an area that looks extremely interesting, we have basically a sample acquisition system that includes an auger that will allow us to bring some subsurface material quickly to the surface so that the near IR can look at it. Is there water ice present in that top, say, 30 centimeters? Or we have a coring drill that allows us to take a sample down to 1 meter. Once we have that core, we bring it to our oven, which breaks up that core into 8 segments, heats each one of the segments up to basically 150 degrees C, sends it to our GC mass spec, which also has a near IR to it, and we can evaluate the volatiles. As part of this instrument, we also have a freezing device, a cold finger, that any water that's been released can be frozen and imaged as well. And then there's a mobility aspect to this that the Canadian Space Agency is providing. So what I did on this particular chart was I looked at the instrument suite that was put on the RLEP-2 mission. I kind of consider that the platinum mission because it basically had a huge set of potential instruments that the RLEP-2 instrument team recommended for that 6 months to a year in a permanently shadowed crater. The Resolve instrument suite currently has several of the instruments, not obviously the full range of them. That mission had both lander instruments and mobile instruments, and so for Resolve, we're all on the mobile platform at the moment. The lander pretty much dies after it lands under the current situation. We have a 1 meter drill. They talked about a 2 meter drill. And we have some mineral aspects associated with our instrument. If you look at the Luna 27 mission, that's basically a lander alone. There may be a rover that goes with that mission, but I doubt it will have a drill or any subsurface probing features to it. But it has a suite of instruments for both mineral as well as potential volatile analysis. And then what I call the optimal prospector, where you have a slightly larger instrument suite potentially for your mobility aspect. That might be something that we would use for that more sustained or assessment, expanded assessment. So one thing that we might look at from a future mission perspective is doing this short duration mission. I call it Resolve Package 1.0 and Polar Rover 1.0. when you're doing this exploratory assessment for a short period of time, if you find a location that you like, a more focused assessment might be required. So now I want to have a polar power processor because I'll want to spend more time in the shadowed region than this Resolve mission, which is looking at a short duration sunlit place. And then maybe upgrading the instruments, but not starting from scratch. So a lot of the risk for this kind of longer duration or RLEP-2-like mission could be reduced by doing this short duration mission. And then if I really find that resource is distributed and understood fairly well, and I understand the material well, I would go into more of an ice miner mission where I'm now adding hardware to go through the whole mining process, the excavation, the processing, the separation and storage, and doing that at a rate and a scale that is representative of what a human mission might want downstream. So this is a possible pathway. You know, I started the presentation with this notional stepping stone approach. Here are two potential missions that NASA might pursue. The resource prospecting mission that I was talking about, there's been a lot of talk about asteroid retrieval and utilization missions. I don't go into the details here, but there are actually a lot of technologies that go into both of these that may be similar from a subsystem perspective. Obviously, the gravity is the biggest concern I have difference between the two, and that will require a significant amount of extra work for the microgravity environment. But some of the things we're looking at is from this first mission, we might go down the pathway of the moon in terms of do I go for the poles or do I just go for oxygen from the regolith? You know, how we built the lander could help sample return missions. Some of the things that we're looking at, water on the poles, I'm extremely interested, and the ISRU community is extremely interested in water on Mars. How is it distributed and such? How deep is it? Am I allowed to actually process it with the planetary protection folks? That might lead to a Mars sample return mission that utilizes ISRU and eventually takes us to human exploration of Mars. And with that, I'll come to my conclusion.